Okay, hello everyone. I'm Naik from the Institute of Astronomy in Cambridge. I'm coming to the end of the first year of my PhD, supervised by Puchwein and Christine Davis. And I'm going to be talking about the project I've been working on since January, which involves looking at galaxy rotation curves in FR gravity. So, one thing I should say at the beginning is that I can't actually see this point very well, so it may well happen that I'll be talking about a feature and pointing at a different feature, so I hope you're all switched on. So here are some observed rotation curves from the Spark sample. And I'm showing you these because each of these 4 rotation curves is suitably cherry-picked because they display an upturn like this. So it has been observed more generally that galaxies, particularly at low redshifts, do display such upturns. So in this talk, what I'm going to demonstrate is basically one key result, which is that from simulations, we expect Milky Way-like galaxies in chameleon FR gravity theories to display exactly this kind of upturn. So before I get on to showing you the simulations, I'll just briefly go over some of the most relevant theory. So as Hans pointed out in his talk, the governing equations in modified gravity n-body simulations are this modified Poisson equation and also a field equation for a scalar field. So in this case, our scalar field is this quantity fr, which is the derivative of our function f of r. And what happens is that in practice, by choosing a function f of r, that's tantamount to choosing an effective potential for your scalar field. And so the game is to choose a function f of r such that you have the chameleon screening mechanism. So the other relevant equation is this one, which highlights the fifth force contribution. So this is, again, this will be familiar from Hans's talk, but the fifth force contribution is proportional to the gradient of our scalar field. So the chameleon screening mechanism works by having an effective potential such that in regions of high density, this gradient is suppressed, so that in regions of high density, you don't observe the fifth force and your modified gravity is screened. So let's choose a function f of r. So the form we've chosen is this form, the Hu-Sawicki model. So it's got 3 parameters, n, c1, and c2. And so we take n equal to 1 for an easy life. And we also demand that this be true in order to mimic the lambda CDM expansion history, the background expansion history. And so what we're left with is one parameter, either c1 or c2. And so it can be shown that this is the case. So we're taking c2 as our free parameter, and we can reframe it in terms of this quantity. So recall that fr is our scalar field. So this over bar means that we're taking the cosmic background value, and this 0 indicates that we're evaluating it today. So this now is the remaining free parameter of our theory. So this is the parameter I'm going to be inputting into my simulations. This is the parameter I'm going to be talking about. So the limit where you take that to 0 equates to the lambda CDM limit. But also what we'll show is that for a given galaxy, the location of the screening radius, or in other words, the location of the upturn on the rotation curve, is determined by your choice of this parameter. So a bit about the code. The code I've used is called MG-GADGET. It was developed by my supervisor, Puchwein, and he's going to be here next week talking about it. But in brief, I'll say a little bit about it. So it's implemented as a module within the n-body code GADGET 3, and the way it works is using an adaptive mesh. So that's illustrated here. So these blue particles are the GADGET n-body particles, whereas these red lines form the space-filling adaptive mesh. So in the regions where the n-body particles, the blue dots, are densely populated, that corresponds to regions of high density in our simulation volume. And what we have is that the adaptive mesh then has a finer resolution. And conversely, in regions of sparse and population of n-body particles, you have a coarser grid resolution. And so this is perfect for our purposes because we want to look at the inner regions of galaxies where we expect some of the highest densities in our simulation volume, so these screened regions of galaxies. And so that's where we're going to have, where is this pointing? That's where we're going to have the regions of highest grid resolution. Another thing to say about this is that so Gadget's classical Poisson solver in sort of regular lambda CDM Gadget works by using a hierarchical octree. And the way this mesh is constructed is by constructing this adaptive grid using the leaves of that tree. The point being that this module is sort of implemented in such a way that it slots very neatly into Gadget's existing framework. So now that we've got an adaptive grid, what do we do with it? So I showed you these governing equations earlier, and these two equations complete the set, and they come from having chosen the Hu-Sawicki model. And so what we do is we discretize these equations and solve them on the grid using a numerical method. So the method that MG-GADGET uses is a Newton-Gauss-Seidel method, which is sort of conceptually similar to a Newton-Raphson method. And now the problem with this is that the traditional lambda CDM Poisson solver uses various methods. So it uses the octree that I mentioned earlier, and it uses fast Fourier transforms. And these methods are super fast, but they rely upon the linearity of Poisson's equation because they rely upon the principle of superposition. And now by having these nonlinear equations, we've thrown those methods out the window. So we're stuck doing this very slow Newton-Gauss-Seidel method. So as a consequence of this, we're not yet at a stage with modified gravity n-body codes where we can do full galaxy simulations because it's just too computationally expensive. So what we're doing here instead is we're taking lambda CDM simulations of galaxies and using them as toy models. So essentially we're taking these toy models and using that F of R solver in post-processing to see how the scalar field behaves on these galaxies. Now, these toys that we're using are quite expensive ones. So these three galaxies are the ones we've looked at in particular, and they're from the Auriga project, and that's the project paper, Grand et al. And these are state-of-the-art simulations. So they have carefully calibrated prescriptions for galaxy formation, for star formation, for AGN feedback, for stellar feedback. And they also have magnetic fields because they have an onboard MHD solver. So, so you might very well ask at this stage, well, are the results still valid? So to what extent do these lambda CDM formed galaxies resemble F of R galaxies? And that's a valid question. We don't know for certain. And so this is an intermediate step, but nonetheless, there is evidence to suggest that we don't expect the galaxies to look that different. So these are simulations that Christian Arnold did in his 2016 paper. But so I've generated this plot using them. So also, I generated this plot before I sort of changed my signature color scheme. So that top color, I would now. This is called gold, and this is called dark magenta. But so I would now go for goldenrod and dark orchid. So if anybody knows what they are, then I'd encourage you to imagine those instead. So what these plots are so starting from the same initial conditions, Christian Arnold simulated dark matter only, so dark matter halos, using under lambda CDM and under F of R gravity. And so these are full F of R simulations. And what we observe is that in both cases, the dark matter halos you get are reasonably well fit by NFW profiles. In cases where the fit is not so good, you observe that in both F of R and lambda CDM. And in some cases, it would appear that actually the fit is even better in F of R than it is in lambda CDM. So that's some evidence to suggest that maybe this method with the toy models is not such a bad one. but ultimately we don't know what the baryons are doing. So, without further ado, let's look at how the scalar field behaves in our simulations. So this is so I showed you those 3 galaxies earlier. So I'm using the same numbers that the Auriga project has. So this is Galaxy 24, this is Galaxy 16, this is Galaxy 9, and they're all supposedly Milky Way-like galaxies. So here's Galaxy 24, and what we observe is, so this plot on the right are density projections, and these plots on the left are maps of the scalar field. So these are face-on and these are edge-on. And so what we observe is that there's a very sharp screening radius. If you live out here, you experience the 5th force, whereas if you live inside this radius, then it's completely screened. Now this, when we look at it edge-on, we see that it inherits the disk structure of the galaxy, which suggests that the baryons play a large role in determining where the screen radius lies. So I've not included length scales in this, but as I said, the position of that screening radius depends on your input parameter, and we'll look at that more quantitatively in a moment. So here's Galaxy 16, and we see exactly the same profile. Here's Galaxy 9, and for the same value of the background field, we see that the screening radius is much further in, reflecting the morphology of the galaxy. So here are some plots for the field profile. So this is for Galaxy 16, and I've taken 3 different background values. So for this value, 2 times 10 to the minus 6, which is the strongest f of r, we find that the galaxy is completely unscreened. Wherever you live in this galaxy, you experience the 5th force. Whereas for these 2 values, we see that you do have a screening radius. If you live inside that screening radius, the 5th force is entirely suppressed. So where am I pointing? There. So there are fluctuations in the field, but nonetheless these values are so small that the gradient is still completely suppressed. The 5th force is very small indeed. So yes. And another thing worth pointing out is that if this galaxy were our Milky Way, then the difference between this background value for the scalar field and this background value is the difference between screening our solar system and not screening our solar system. So let's look at some rotation curves. So this is for the background value of 10 to the minus 6. And what we observe is, so the solid lines, so the 3 colors correspond to the 3 galaxies. The solid lines give the solid lines exclude the 5th force, whereas the dashed lines include the 5th force contribution. And so what we observe is for these 2 galaxies, galaxies 16 and 24, we observe these marked upturns, which would be observable. Whereas for Galaxy 9, there's still an upturn, but because of where it is, that wouldn't be observable on a observed rotation curve, because it happens while the rotation curve is still rising. And as I said earlier, that reflects the morphology of the galaxy. So here's Galaxy 24, and we observe the rotation curves as we vary the background value. And as I mentioned earlier, varying the background value moves the screening radius further and further out. So for this value, 10 to the minus 7, which is the weakest, the curve is completely hidden by the Newtonian curve.
Sorry.
Yeah.
Values are consistent with the universe acceleration?
Yes. Yeah.
So they obey the limits.
Yeah, absolutely. So yeah. And so now we observe a similar thing for Galaxy 16. For the strongest value, it's pretty much unscreened all the way in. For the intermediate values, we observe these upturns, and for the weakest value, it's again overlaid by the Newtonian curve. Galaxy 9, meanwhile, this was the one with a slightly different morphology. For most of the values of for these 2 values of the background field, we have the rotation curve rising as the we have the upturn happening as the rotation curve rises, yielding sort of unobservable upturns, whereas for a slightly weaker value, we do have this observable upturn. So that is basically all. So what we have is that these simulations demonstrate that in chameleon FFR gravity, you'd expect rotation curves to display such upturns. So we've not yet done a sort of quantitative comparison to observations, because actually the question is quite tricky, because you look at a rotation curve, and the position of the upturn is determined by both the background value of the scalar field, which you want to fit, and also the matter distribution of the galaxy. And so the baryonic component of that, the gas and the stars and the dust, you hopefully would constrain observationally, but the dark matter you need to fit as well. So firstly, there's a question of how to do that. So we've demonstrated that NFW perhaps is as good a fit for FFR as it is in lambda CDM, but perhaps that's not the case when baryons are included. The other question is also how to actually do the parameter fit for FR naught, because for a given matter distribution, running this clunky 3D solver to get to FR naught is quite computationally expensive. So what would be better if there was some sort of semi-analytic model or perhaps some numerical fix? So yes, that's basically everything. Have I got any time? Or? No, it's okay.
Thanks a lot.
Questions? Oh, loads of questions.
Have you thought about looking at the motion of stars perpendicular to the plane of the galaxy? If your screening radius is this kind of pancake shape, I don't know if they, or maybe with the new data sets from Gaia, maybe they go out far enough that you could start to see it in that direction as well?
Yeah. So we did actually think about looking at the Gaia data set to try and think about how things are behaving within our own galaxy, but actually it's kind of a complicated question, because while you do have the stars, it's quite difficult to have everything else. But in terms of thinking about the motion perpendicular to the plane, I've not really given it much thought, no, but that's an interesting question.
So at the beginning of the talk, you showed 4 examples of real galaxies.
Yeah.
And they all have a bump that, according to what you say, could be a detection of modified gravity.
Yes. Yeah.
The question is, is the FR naught you need to explain these 4 galaxies the same?
Yeah, that is exactly the question. Yeah. So when we do this parameter fit, the signal that we're looking for is to get a consistent value of FR naught across our whole sample, and that would strongly favour FR gravity. Whereas if we're getting disparate values for FR naught for every galaxy, then we could go back to blaming baryons. But so yeah, that is.
So you
the
could
question,
actually, if you get different FR naught values, you can actually use these 4 galaxies to rule out FFR, or to rule out that part of the parameter space.
It would disfavor FFR, yeah, because you do want a globally consistent value for FR naught, yeah.
Isn't it more complicated than that? All these different galaxies live in different environments, so the background value of FR naught should be different.
Yeah, that's true. So we're planning on doing some work to quantify the extent of that effect, the extent of the environmental screening. Yeah.
Yeah, I was just wondering, can you resolve substructure? Can you do profiles for substructure, like dwarf galaxies or something?
Yeah.
Because it could be interesting to look at the profiles of the dwarfs that are outside of the screening radius. In principle, you can get the same kinematic effect. They could even, well, in a way, solve the core cusp problem, because you would say could get apparently chord profiles.
Yeah, that's true. And so in fact, Galaxy 16 sort of just outside of most of the plots I showed you does have this small satellite, which for most reasonable values of the background field is unscreened. So yeah, that's true. And substructure is interesting. Another thing with the core cusp problem is that this business of explaining these upturns and the rotation curves with f of r gravity could actually help us out quite a lot with the core cusp problem, because a lot of our belief in cores comes from these rotation curves. And so if we're explaining the outer bits of the rotation curves with f of r gravity, perhaps we don't need cores anymore in the interiors, potentially.
Actually, 1+1 questions. So this effect comes from the fact that the gravitational interactions that forms the galaxy changes, or that the gravitational interaction that causes the acceleration of the universe changes?
This effect, the upturn. So it comes from. It's not the formation of the galaxy. It comes from the gravitational interactions within the galaxy are augmented by this fifth force at regions beyond the screening radius.
So the dilution of the gravitational modification doesn't play any role, right? I mean, the acceleration of the universe.
No.
Okay. Then my second question quickly is the following. Are there any degeneracies? Because there are works in the literature that's saying that you could see these effects in clusters of galaxies. However, an error saying the estimation of the galaxy mass by 3% will cover the effect. So is it a clear signal or not?
So we're not sure yet. As I say, we've not done a quantitative parameter fit. I suspect there will be a big issue with degeneracies. Yeah.
Okay, so we'll move on. Thanks a lot.